That'll do. Excellent. Okay, so welcome to the last two exercises. We've got a bit to go through, but it shouldn't take longer than 20 minutes based off of last year's videos. So we have the area between functions. This is a skill that we learn in methods. And if we have two functions, okay, so if we have f of x and g of x, then the area between them is the integral from their points of intersection. They intersect at a and b of the top function, take the bottom function with regard to x. Okay, so if we want to find that area in there, it's just going to be the area of the top function, take away the area of the bottom function. It's a skill we learn in methods. Maybe I'll just explain really quickly why it's true. If we just do the integral from a to b of f of x, okay, that's going to give us this area here, right? And if we just do the integral from a to b of g of x, okay, it's going to give us this area here. And so if we do this area, take away this area, we're going to be left with that component of it. All right, so that's how it works. Very good. Let's get into our example. So we have determined the exact area between the function f of x and g of x. I've graphed both of them, and we can see very clearly that the red function, x plus cos x take 1, is the top function. We can see they integrate at 1 and 2 pi, so we're going to find the area of that region. So our first step is going to be to write the integral statement. The area between these functions is going to be the integral from 1 to 2 pi of the top function, which is x plus cos x, take 1. Take away the bottom function, which is x cos x. All of that is with regards to x. Now we're not learning really any new skills here as such. We're just applying a method skill in a specialist context. So all of that we can integrate using methods techniques. Over here we're going to have to use integration by parts. Okay, so let's perform the integral and get it applied to our fundamental theorem of calculus. The integral of x is x squared on 2. The integral of cos x is sin x. And the integral of 1 is x. So that's all the first component, okay? The first function, our top function, that's what it integrates to. Take away, okay, so there's our top function. Take away, and we want the integral of our bottom function. Now, in order to do that, I'm going to use integration by parts. So I want the integral of x cos x. And so the formula for integration by parts is integral of u v dash is uv take away integral of u dash v. Or I've written that around the wrong way. I think I've got u around the wrong way.
No,
That's spot on. Excellent. Okay. So remember, we want u to be easy to differentiate and v dash to be easy to integrate. Now both of these are quite easy for us to integrate and differentiate. However, all right, in here we're going to have the integral of u dash v. And so I'll just show you, if I put x as v dash and u as cos x, okay, derivative of cos is negative sine, integral of x is x squared on 2. If we process this one, we're going to end up with x squared on 2 sine x, which we would have to perform integration by parts again to solve. So this manner is not going to work for us. We need to readjust it, which means, and you'll just get it through trial and error if you can't see it, which means we're going to set u as x and v dash as cos x. Now the integral of cos x is sin x, and the integral, the derivative of x is 1. Now it's going to work nicely for us. So the integral of x cos x make sure you got that right, u dash v dash. Yep, is uv x sin x, take away, and then we have the integral of u dash v, which is just the integral of sin x. So this component is much more pleasant for us to just evaluate in one step. And the integral of sin x is, of course, negative cos x. So the two negatives make a positive, and then we would have our plus c for a indefinite integral. However, all we're doing, the reason we've evaluated this part for integration by parts is we wanted the integral of that component for this definite integral. So we're just going to take that real part and plug it right here. It is x sine x plus cos x. And we're integrating from 1 to 2 pi. All right. And so straight away, we'll just substitute in the upper boundary. We're going to have 2 pi squared on top of 2 plus sine of 2 pi. I'm going to write out the whole thing. Take away 2 pi. All right, take away 2 pi sine 2 pi plus cos of 2 pi. Okay, that's what we get when we sub in our upper boundary. Then we have to take away what we get when we sub in our lower boundary, which is going to be half plus sine of 1, take 1, take 1 sine 1 plus cos 1. Just get a square bracket. And then all we're going to do is collect like terms and simplify as we can. So what have we got? Any sine of 2 pi anywhere on the unit circle, okay? We've got 2 pi, that's here. The sine value is 0, so that's going to 0, that's going to 0. Cos of 2 pi, that simplifies to positive 1. And so let's just start to simplify each component. This is going to be 4 pi squared on 2, which will just be 2 pi squared. Here we have take away 2 pi. Here we have 1. All right. Here we have half. Now we have sine 1 take sine 1, so those parts will cancel. They're like terms. So we have, what have we got? We've got take away half. So let's not forget that's a negative there. That negative is going to distribute. Take away half plus 1, and then take cos 1. All right, so a bit of a mess there, but we're asked to find the exact area. What have we done?
So even though the integral for x cos of x is definite, when we integrate it by parts, it's no longer definite?
So this here is the correct solution to this statement, okay? So all we've done there is found that's the indefinite integral of this one here.
Isn't that a definite integral though, because it lies inside?
I haven't stated a boundary here. It's only if you state a boundary that it becomes a definite integral. And so we only evaluated this for the purpose of plugging it in here. So technically it's not a definite integral. Like you're not going to get subtracted marks anywhere there. The only reason we're doing that is so we can plug it in.
Yep.
Good question. Okay. All right. And then the only thing that's simplifying is here, isn't it? We've got plus 1, take a half, and plus 1. So what's that? 3 on 2. So we've got 2 pi squared, take 2 pi, 2, take a half is 3 on 2, and then take cos 1. Area, units squared. All right, that's going to be our answer for 7, the first question there in 7E. So quite long. This is a good example of something similar to what you get in an exam, either be an area or a volume calculation, where they do expect you to plug things in using the fundamental theorem of calculus and just process it. We've got the integration by parts there, so we're including the spec skills. All right, any questions about that one? Okay, so in that exercise, the opportunity for you guys to do it, we're just doing the integral of the top function, take the bottom function over those boundaries. Just make sure we're using step techniques rather than, well, you'll have to. All right, let's move on then to the volume. Okay, yeah, Slats has done his wine glass folio. Jack, you've done a little bit of it, your methods folio.
Yeah.
How about you guys?
Oh, tiny bit.
Tiny bit?
Yeah.
Have you done some volume calculations?
Yeah.
Excellent. Okay. So, let's go through these questions though. So we've got 2 things that we're going to talk about here. Maybe I'll just say very quickly, this is what the methods folio is about, is if we have a function, and what we're going to do is rotate that function around the x-axis. You can imagine it as someone standing on the x-axis, looking at the point of origin, okay? To them, this function is going to look like a dot, and if you rotate a dot around the x-axis, all right, maintaining the f of x distance, you're going to get a circle. And the area of a circle is pi r squared, where r is the distance for the function. So what we get then, and then we have the cross-sectional area multiplied by depth gives you volume. Okay, so we have the volume is equal to the integral from a to b of pi times f of x squared. Okay, with regard to x. So this is the formula for the volume of a solid that obtains when you rotate f of x around the x-axis. So you can think of it, if we rotate this function around the x-axis, this is the solid we're going to get, and it's going to give us the volume of this solid. What is volume? Okay, well we know area is how many square units fit inside a two-dimensional shape. Volume is how many cube units fit inside a three-dimensional shape. Alright, find the volume of the solid formed when the function f of x is 3x squared plus 2 is rotated around the x-axis from 0 to 3. So, from 0 to 3, of pi times the function squared, our function is 3x squared plus 2. Okay, integral from a to b of pi times the function squared. That's all we're processing. Now, at this point, you can type that into your calculator, right? Let's demonstrate the skills using the fundamental theorem of calculus, because here, a number of students, historically, they've just gone, oh, yep, squared, squared. You have to perform perfect square rule. You have to expand that. So, what it is before we integrate it, all right, we're not ready to integrate it yet. We must perform the perfect square expansion. It's going to be pi multiplied by 9x to the 4, okay, that component squared, a squared, plus 2 lots of a times b. So it's going to be 2 lots of, I'll write it out slowly, 3x squared times 2, okay, a squared plus 2ab, and then plus b squared. With regards to x, now pi, we can pull that right out the front of the integral because it's a constant. So we simplify our calculation a little bit. And so I won't write the integral, yes I will, because we need to evaluate that. 0 to 3, we'll have 9x to the 4, 2 times 3 times 2, that's 12x squared, and plus 4. Okay. So now we're ready to integrate. Why? Because we've fully expanded it, we've expressed every term in the form x to the power of n, so we're ready to integrate. So let's apply the fundamental theorem of calculus. We've got this pi sitting up front. Now, integral of x to the 4 is x to the 5 on 5, and we've got that 9 hanging out the front. Integral of x squared is x to the 3 on 3, integral of 4 is 4x, and that's from 0 to 3. Alright, then we'll plug in 3. And this can be simplified and so forth. Now, when you sub 0 in, that's going to 0, that's going to 0, that's going to 0. So we have the upper boundary, take away the lower boundary is just 0. And now, I think the best thing to do is just evaluate that in your calculator. And, you know, like, be smart about it. Don't type in this expression, because look how fiddly it is, look how easy it is to make an error. All right, type this one in, okay? Because the answer to this is going to be the same as the answer to this. This is much easier for us to type in. So, option calc integral. If you're not sure how to do that, I'll come show you. We've got 3x squared plus 2, and that's squared from 0 to 3. Alright, so pi times 2787 on 5. And we can evaluate it to a few figures. 1751 units cubed, which to 3 significant figures would be 1750. Alright, check the good.
I don't know what any of those things.
Alright. one's going to be a bit tricky then if you're a bit stuck. How about you guys? Do you find that okay?
Yeah.
Yeah, Haley? All right, what we might do is pause there then, and I'll just make sure that you're feeling all right. Going to be a little bit trickier.
Patterns in the video.
So what we're doing now is, so there we were doing rotating functions around the x-axis. Now we're looking at rotating a relationship around the y-axis, okay? So this is the relationship we have, x squared plus y equals 7, and there's a plethora of ways that we could present that, right? We could present it as y equals 7 take away x squared, but we could also rearrange it so that we have x squared equals 7 take y, and so we could have x is plus or minus the square root of 7 take y, excuse me. And we're just interested in this component of it because we're going to rotate that around the y-axis. And we think that's going around the y-axis like that. From x is 1 to x is 7. Okay, so the formula for this, what we're going to do is we're going to integrate from c to d, okay? Where c is equal to the y value at x is a, and d is equal to the y value at x is b. All right, so you know how we integrate from x is 1 to x is 7. So we're going to go, that's going to be our c value, and that's going to be our d value of pi multiplied by the function of y squared. The function of y squared. So the function of y squared is going to be this one. We can often call it like x is equal to some function of y, like how we have y is equal to some function of x. All right, so the function of y is going to be this one here. All right, so what we're doing then, first, let's evaluate what's going on here. We've got when x is 1, what's the y value? And when x is 7, because we want to know what's those y values over which we're performing the integral for. So we would have when x is 1, the y value is going to be 7 take 1. And we'll have when x is 7, the y value is 7 take 7 squared. 7 take 49 minus 42. What we're going to integrate from then is, sorry, I think I said it around the wrong way before. We integrate from the lower value of y to the upper value of y because we want to integrate in a positive direction. From the negative values of y to the positive values of y. All right, so we're integrating from minus 42 to positive 6. So the volume then, the volume is pi multiplied by the integral from minus 42 to positive 7.
Where did you get 1 and 6 from?
1 and 7.
Oh, yeah.
Yep, those are the x values over which we're required to integrate. It says find the volume of the solid formed when the area bound by this relation from 1 to 7. All right, so from 1 to 7 when that's rotated around the y-axis. Okay, so the function of y then is this one here. It's the square root of 7 take y squared. Okay, so we have the integral boundaries, we have pi, and we have the function of y squared. And because we have a function of y, we're integrating with regards to y. Okay, just like before we would integrate with regards to x, now we're going to integrate with regards to y. So the trickiest part of this, right, is setting up this statement. Once you have this statement, it's just a matter of processing it. Okay? So the square root and the square will cancel. So we're doing the integral from minus 42 to 7 of 7 take y with regards to y. It's going to be we can process that now. 7y, take away y squared on 2. Okay, we're just integrating the variable y with regards to y. Minus 42 to 7. Minus 42 squared on 2. Put those around the wrong way. Sorry, 7, 7, positive 7. Now we'll go through our minus 42. Alright. Now again, I'm not going to type in that bunch of hogwash into my calculator. All I'm going to type in is this statement here. Just do it quickly in my head. 1200 units cubed. So, okay. So, what's the tricky part? The tricky part is expressing it as a function of y. So we have x equals. That's the part that we're substituting. We're always integrating from the bottom to the top. We're integrating in what we call the positive direction. So we must identify these corresponding y values. All right, so you know those are coordinates, aren't they? This is 7 and minus 42. This is 1 and 6. Okay, so is that skill seem all right? Excellent. All right, cool. Because it gets a little bit trickier again. Do you want us to pause for a bit and you get that down, Jack?
Yes, please.
Yep. Cool. All right, so just like before, where we would find the area between two functions, now what we're going to do is going to find the volume between two functions when this area here is rotated around the x-axis. All right, and we're just using the formula presented to us here. It's just pi times the integral from a to b of the upper function, fu, take away the lower function, fl.
I said that.
Okay? And of course that's going to be the case. We know we can integrate term by term. Like if you just did the top function, okay, it's going to give you that volume. If you just did the lower function, it's going to give you that volume. And so then the top volume, take the lower volume, leaves you with that leftover component. And we're rotating around the x-axis. You do also do these around the y-axis, but we're rotating around the x-axis in this circumstance. It says, find the volume that obtains when the area bound by x is 1, the function x on 4 squared, I've simplified that straight away to x squared on 16, and the function 1 on x is rotated around the x-axis. Okay, so the lower boundary of our integral is 1. But we don't know what the upper boundary is yet. And so the upper boundary is going to be this point of intersection. We can g-solve it or we can calculate it. These two functions are going to intersect when they equal one another. When x squared on 16 is equal to 1 on x, I'm going to multiply both sides by x, and then multiply both sides by 16, and then cube root both sides. Okay, so they intersect when x is 16 to the power of the third. So that means our upper boundary here of the point of intersection is 16 to the power of 1/3. So we have our lower boundary, we have our upper boundary. Okay, so the volume is the integral from a to b of pi multiplied by the upper function squared. Okay, the top function, the one at the top, we'll look at our graph. The one at the top is 1 on x squared. Okay, top function squared, take away the lower function, x squared on 16, squared with regards to x. Okay, that's it. The tricky part here is just setting it up, isn't it? You know, once we've set up that integral statement, you're just away to the hills performing your algebra. All right, first let's simplify it, and then we can integrate. So we maintain our integral here, pull pi out the front. Now 1 on x squared is the same as, I'm going to write that as x to the power of, would be 1 on x squared. I'm going to write it as x to the minus 2, take it to the top so it's ready for us to integrate. And this one is going to be 1 on 16 multiplied by x to the power of 4. Okay, look how cheese that is to integrate.
Won't it be 16 times 16, like 1 on 16
Oh,
squared?
yeah, spot on. Good pickup. Look how cheese that is now to integrate. Okay, so we'll plug in fundamental theorem of calculus, that pi is hanging out the front. X to the minus 2 goes to x to the minus 1 on minus 1. We have this 1 on 16 squared hanging out, and x to the 5 on 5. From 1 to 16 to the power of third, 1 on 3. Okay, we'll type it out. A lot of copying going on, isn't it? You're just copying what you've written, but changing the number, and then take away, and we just have 1. Okay, and again, I'm not going to type that in, we'll just evaluate it on our calculator. So, as far as what steps are you required to show, you have the integral statement, you have the integration, you have the fundamental theorem of calculus, and then we'll have an answer. And that's perfectly adequate, unless it says find the exact answer, in which case you do have to process it a bit. So we'll type this into our calculator. From 1 to 16 to the power of 1 on 3 of x to the minus 2 take 1 over 16 squared x to the 4 and then multiplied by pi. 1.647 1.65 units cubed. Very good. Okay, feel okay about that one?
Yeah.
Yeah, slats, same? Good. Yeah. Excellent.